Okay, so I realized after ending that last recording, because the time limit is 15 minutes, I found the mistake. I knew something was going wrong. So here's V1, and then I just switched to V2. Yeah, here for no reason. So let me correct this. So this is all going to be wrong. This we don't need. Okay, so I wanted to leave that just to point out the error at the end of that video, but so now we can correct it. So this should be V1, which is this -1, 1, 0. So now this is -1 plus 1/2. So that's correct. 0 minus 1/2. So this is incorrect. And 1 minus 1. Nope. 1 minus 0. Okay. So this is -1/2. This is 1. Okay. So our orthogonal basis is V1 is -1, 1, 0, and V2 is -1/2, -1/2, 1. And it's always nice to pause and check that you didn't do something thoughtless like I did there. So let's see. If we do the inner product now, or the dot product, we get +1/2, -1/2, so that'd be 0, plus 0. Okay, good. These are orthogonal vectors now. Great. Then, let me pause. Okay, but unfortunately, for things to come out nice and neat the way we want, so there's a lot going kind of behind the scenes in this whole process. And for things to work out the way we want them to, what we actually need is an orthonormal vectors. So we're going to have to normalize each of these vectors before we set up the columns of that matrix P. So we got one more bit of what might feel kind of like busy work to do here. And actually, let me pan up a little bit. So the vectors we're going to use are this guy, 1, 1, 1. And I know, I see I've got V1 here. I'm going to change the name here to V -8. Because it corresponds to that eigenvalue -8. And then I'm just going to call these guys V1 and V2, just for simplicity, because V13 1 and V13 2, I don't really want to do that. Okay, but these are the three vectors we're going to use. We just need to normalize them. We've actually accomplished everything in this process up to step 4. So now I'll call these here U -8. Which to normalize a vector, you just have to do 1 over the length of that original vector times the original vector. That's how you scale the length down to 1. So the length of the length of a vector is the square root of the sum of the squares of all the components. So it's going to be 1 squared plus 1 squared plus 1 squared. This is the length of V8, here, or the norm of V8. So that's the square root of 1 plus 1 plus 1, so square root of 3. And so this is 1 over the square root of 3 times that vector. So our U -8 is 1 over square root of 3, 1 over square root of 3, 1 over the square root of 3. We get some hideous vectors in this process. And that's another reason I wanted to keep your homework short. All right. So now we'll call this U1 and U2. So this is going to be 1 over the length of V1 times V1. Which the length of V1 is, this guy squared is 1 plus 1 plus 0. So square root of 2 times this vector. So that's -1 over the square root of 2, 1 over the square root of 2, 0. And then U2, 1 over the length of V2 times V2. I'll move this up to give myself room. Oh, I need to see V2 though. Okay, length of V2. I guess we don't need this anymore. got fractions here, so I'm going to do the length of V2 off to the side. So that's the square root of the squares, sum of the squares of each entry. So -1/2 squared plus -1/2 squared plus 1 squared. So that's -1 squared over 2 squared. Same deal here. And then 1 squared is 1. Since these are written in terms of fourths, I'm going to write that 1, the 1 squared, which is 1, as 4 over 4. And just that way we can think through the addition a lot easier. So since they have a common denominator, so I'm going to shorten that radical there, then this is equal to 1 plus 1 plus 4, so that's 6, over 4 plus 4 plus 4, well, okay, so that's 4. And then we could do square root of the top over square root of the bottom. Okay, so the length of V2 is square root of 6 over 2, so 1 over the length of V2, we want the reciprocal, that'll be 2 over the square root of 6 times V2, which is -1/2, -1/2, 1. Okay, so if you distribute 2 over the square root of 6, when you do 2 over the square root of 6 times -1 over 2, the 2's are going to cancel. The negative will still be there. The 2's are going to cancel, and you'll have 1 over the square root of 6. Same exact thing here. 2's cancel, -1 over the square root of 6. And then 2 over the square root of 6 times 1, so... Okay. And I guess I'll leave it like that. Alright, so this is U2. Okay, well then we have everything we need. Let me use a different color. So our diagonalizing matrix P has, okay, now the order here, it's not like one order to use, but you just have to be careful that your diagonal matrix corresponds to the order you do in your matrix P. I'm going to use the U-8 first, so that's this guy. 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. And actually, so while I'm doing that, I'm going to also set up that diagonal matrix D, just before I forget. So that eigenvector corresponds to the eigenvalue -8. So I'm going to put -8 in the first position here. And it's a diagonal matrix, so everything else in that column is going to be 0. And in fact, let me set up all my other zeros. But you have non-zero entries just along the main diagonal. Okay, now the next two eigenvectors, so the U1 right here and the U2 right here, both of these correspond to the eigenvalue 13. If you remember that from earlier. Both of them correspond to 13. So column 2 and column 3 should both have a 13 in it, that corresponding eigenvalue. And so that corresponds to these eigenvectors. -1 over the square root of 2, and this is +1 over the square root of 2? I believe so. Yes. 1 over the square root of 2. And then 0. Okay. And then U2, which is this one. This one over here. Okay, and it's a lot of work to check your answers on these, so I tend to not check my answer. But if everything went according to plan, then you should be able to double check. Again, I mean, I don't know if you want to do it because it's a lot of effort. But the if you multiply P times D times P inverse, and you'll see in the notes that for a symmetric matrix, this is going to be the matrix is orthogonal, which means P inverse is the same as the transpose of P. If you multiply those matrices out, so this matrix P times this matrix D times the transpose of that matrix, you should end up with the original matrix A. That's a lot of matrix multiplying. I guess more realistically, if you had a graphing calculator and you wanted to take the time to type all this in, even that is a lot of effort. But then you could double check your answer that way by entering the matrix into a graphing calculator and then entering this P times D times P inverse and see if you get the matrix that you started with in the problem, in this case, without the minus 13s, this matrix here.